This video is a part of a course on food physics. Of the course, this is a part of the theory section. And of the theory section, here we discuss deformation. So how transport happens in a deforming system. So this is about poromechanics in the food. And the immediate preceding section gave more basics of the poromechanics. And so this one will be sort of more customizing to food, getting closer to food, still general. And then the following one would be talking about the multiple driving forces in food. So until now, we have done the most basic equations for deformation. Now, when these are solved in a computer, there's a lot of variables and details of computing that come into the picture, which can be very overwhelming. And so it's nice to get a big picture of the overall computation. And so this slide is just trying to provide that big picture. So you note that after the basic equations, we determine what are the driving forces for deformation. What drives deformation? What is the load? Then we get details of the material. So strain, energy, density function for the material. Then we combine these two and solve the governing equation. And so the governing equation basically or eventually gives the displacement after solving. From the displacement of the solid, we get velocity. Very important. We get the velocity of the solid. And that velocity of the solid is then included in transport, or the velocities in transport get modified because of the velocities in the solid. So this is the conceptual framework over which we are working, and this is also the computing framework that we would be following. So now let's look at some more details. Now earlier we talked about driving forces or the loads that cause deformation. These driving forces do not have to be external. For example, in bread baking, these loads are not from the outside. It is from the gas pressure that happens due to evaporation of water or carbon dioxide generation. So it's like a body load, a body force that causes the deformation. So the load here is gas pressure. So in the porous media, then this internal pressures from evaporation are going to provide the load. And so the mechanics equation gets modified this way. The overall the loading, external loading is equal to 0. So the effective stress on the solid skeleton is balanced by the average gas pressure. And that's what causes the gas pressure causes the skeleton to move or deform. Another possibility that I'm going to include later, not as part of this module, is when you lose moisture, then it shrinks. That is also like a body load that is distributed over the entire volume, but it is handled differently. So we're going to postpone discussion of that one to later. So that can be another driving force. So I said in this module, we're going to try to sort of customize a little more the porous media equations in the context of food. And so the next thing we need is this strain energy density functions for the particular food material. So that brings in the material aspect, and we need this strain energy density function, that's this W, to get stress. So this strain energy density function is different for different material. So let's look at a few examples of what strain energy density functions have been used in the food context. Now, to obtain the strain energy function that we just talked about, we characterize materials, and therefore food material is no exception, into broad categories. So three of those categories are elastic, plastic, and time dependent. So for each one, the stress strain relationship is different and is determined by the thermodynamics. The strain in the material changes the internal energy. Based on the strain, internal energy, and the properties of the material, stress can be calculated. So these relationships are complex and of course based on the particular material, and normally we just get these from experiment. So the three groups are these elastic, plastic, and time dependent. Elastic material instantaneously deforms when we apply load, and after removal of load it comes back to its original shape. Now this kind of response can be linear, like it's shown here. So it increases linearly. Uh, um, with strain, and it can be non-linear like this one. So the stress and strain do not increase in the same proportion. This type of behavior is also quite common for food materials. The other type of material is plastic. So if we apply so much load that at some point the material begins to, beyond some stress, the material just begins to flow like a liquid. So an example of that can be melt starch, for example. And this was used in a rice puffing simulation where the rice melts at a high temperature, and then it behaves like a plastic material. So the plastic materials are characterized by two additional parameters: the yield stress and the hardening behavior. Yield stress is the minimum amount of stress that is needed before it starts to flow and therefore does not come back to its original shape. The hardening behavior characterizes how much the material behaves like fluids as opposed to solid. The plastic material may follow linear or nonlinear elastic curve below the yield stress. The last category is this time-dependent response to the load. So food materials, for example, we did this for bread baking. So the bread dough can behave like solid or fluid depending on the constitution or some combination of it. And so this is captured in a viscoelastic model, for example, and the time-dependent behavior of the materials is described using viscosity and a relaxation time. Uh, and so this, as I said, also has been used for many food materials. So we see these different materials here, and their behavior is different. So the strain energy density, the strain energy function from which stress can be calculated, uh, given by this sigma equal to del W del epsilon. And so this W is going to be different for all these materials. And so in the next slide, we're going to see some examples of these strain energy density functions. So now, which material model do we choose? Experimental information is absolutely critical, and that's the only thing that can guide us. Sometimes material behaves very differently based on its moisture content and temperature, for example, and these need to be captured using experiment. So some of the changes in properties, for example, can be captured by how it changes with glass transition. So this choice of the material model has to be done extremely carefully, looking into the literature studies that experimentally characterize different food materials and seeing the similarity between the material we need versus what has been studied. This is often the case because we are unlikely to find experimental studies that are exactly for the same material for under the same condition. And it is possible that the same material can be characterized by more than one material model. So here now are some examples of strain energy functions for different types of materials. So remember, for linear elastic material, we actually derived this earlier. So this is the simplest case. When is it useful? I think it's fair to say that this is a huge approximation. It's really valid for small deformation, and it's not useful for many of the food processes. It could be useful for some very minority of the processes, and it's a good starting point. So here the strain energy was related to some material property, that's the Young's modulus, and the strain. Now as the materials get more complex, or the complexity in the material behavior increases, the number of material properties and the strain measures required to characterize the material also increases. And so here we have some more examples. So then we have this type of material, neo-Hookean, and that was used for meat cooking, and the strain energy function looks like this, that has additional material properties and strain measures. Then we have hyperelastic. This is by far the most common one used in many of the simulations relating to food, and shown here is for a drawing simulation, and so this is the strain energy function for a hyperelastic solid. And then viscoelastic has been used quite a bit. For example, this one work that we looked at dough, in baking of bread, changing of dough as using viscoelastic. We're not including the strain energy function here. The hyperelastoplastic is one that we had to use in case of puffing of a rice grain. So here the rice grain is heated to the point that the starch melts, and when the starch melts, then it behaves more like a plastic, and so we have the strain energy function that is, of course, looking increasingly complex. Now, this is not to imply that these strain energy functions and these characterizations of these materials are perfect, but this characterization was used in at least one research study. So after defining the load and then the strain energy function, we are now ready to look at the complete governing equation that we're going to solve. So before I get started with the details, it says this is the final equation to solve. Well, I'm lying here. It's not the final equation, but it's good to go in smaller steps. And so here we show almost close to the final equation that we're going to solve, and I'll explain what would be left. So first, this is the equation that we derived that relates the effective stress on the solid to fluid pressure. This comes from the equation of equilibrium. Now, this effective stress, or called Cauchy stress, that for computational reason is not solved in exactly that stress, but instead it is changed to this what's called the Piola-Kirchhoff stress. So this is the S is now, this is called PK2 stress. So I want to think of it very simply that I am just transforming the stress into a different system, and because of that, all of these other factors are coming, the F, the deformation gradient, and the J. And so it's still stress relating to the fluid pressures. Now J happens to be this inverse of determinant of F, and so if I plug that in, and then the stress I plug in terms of this strain energy density function. Remember that guy we derived sigma equal to del W del epsilon. We're trying to use that information here. So here we write S is equal to this del W del E, and this is why we discussed W the last slides, the strain energy function that comes based on the particular the material that we chose. So remember, for a linear elastic material, this is half okay, and so in other words, the strain energy function relates to the material property and the strain, and so that's given for a material. So my point is this del W del epsilon is a known constitutive relation that we're using. So then in this equation, if we know the fluid pressures that is driving the deformation, then the only unknown in this equation is F. So we solve this equation for F. Okay, so that's the deformation gradient. Now that F, from that F, we're going to actually get the displacements, but that I'll show in a second. So here it's important to know that we now have one equation and one unknown, and that unknown is F, or the deformation gradient. Now the equation that we just completed, it still has this fluid pressure that is not completely resolved. So we are going to postpone that to a little bit later. But to solve the equation, we need boundary conditions. And the boundary conditions can be of many different kind. It can be just free. So free means a food material is just free to expand or deform in all directions. And it can be some known load placed on it, or it can have some known velocity, or it can have known displacement. All those are possibilities. However, the most commonly used boundary condition in literature, most commonly used boundary condition in literature is this free. And that's not to say that it is the most realistic one for real processes, but that seems to be the one that is used most. It's most convenient, and it's quite a reasonable boundary condition that has been used. So from the deformation gradient calculated by solving the governing equation of equilibrium, then we can get to displacement. So the deformation gradient is related to strain this way, and from strain we get the displacement, that is U. So this is the displacement of the solid that we're now able to have. So from the displacement, of course, we can calculate velocity, and we can calculate other quantities like porosity, because displacement gives what is the current solid volume. So of course, from displacement U, we can get del U del T, which is the velocity. So this is the velocity of the solid phase. And so you can see if the solid is moving and the fluid is moving in relation to the solid, then this solid velocity is going to be important in transport. And we're going to see how in just a minute. So velocity is the important thing that kind of couples the deformation with transport. The other important quantity that we can get out of this deforming solid is to be able to calculate porosity. And to calculate porosity, we have this very important concept that the solid volume is conserved. So this is the volume of solid phase only, not the way we normally are thinking of the solid volume for the entire food, but it's the volume of the solid phase. So let's see how we can write it algebraically. And so if V0 is the total volume of the food, then V0 times 1 minus phi0, 0 stands for initial. So this is the initial porosity. So 1 minus phi0 is the solids fraction. So solids fraction multiplied by the total volume is the solid volume, and multiply by the solid density. So this is not density of the food, but it's only the solid part. And so this is the mass of solid, and that isn't going anywhere. And we are assuming that the solid density does not change. So at any other time during the process, let's say the total volume of the food is V, and its porosity at that point is phi, which is what we are interested in, then V times 1 minus phi is the volume of the solid phase, and then it stays the same. So these two are equal. These two are equal. So from there, because the solid density is not changing, we write V0 times 1 minus phi 0 is equal to V times 1 minus phi. And so if we extract phi, 1 minus phi is 1 minus phi 0 over V0 over V. So this J is the J is V over V0 is the sort of fractional volume, or the change is captured in V over V0. So because I can calculate, I know this V over V0 because I know the entire volume, then I can calculate porosity, and we are able to calculate porosity not just of the entire food, but we can calculate this locally. Okay, so that is going to be very important. So in this step, the solid velocity that we just talked about is included in the transport equation. Let's see how. So as the fluid is moving inside the solid, that's the food, the solid itself is moving, as we have been discussing. So I want to think of the fluid movement as the good old concept of sort of the relative velocity. And I want you to see that the fluxes in, let's say, water, vapor, and others are with respect to ground. So can we think of a fluid that moves inside the solid, okay, and this is just due to transport. This is just due to transport, but the solid simultaneously is deforming, and so the fluid is also it will move due to that deformation. So this additional movement would be due to deformation, and the total movement we can think of as moving due to flow plus the solid structure itself is moving. Now the implementation of this gets into more detail in exactly how we take care of it. For example, the additional flux, it arises because the pressure gradient, for example, in one software or in one formulation is calculated in Lagrangian coordinates. If the pressure gradient were solved in Eulerian coordinate, we don't have to account for this. But these are not the details we need to get in now. Conceptually, then, there's two parts. Fluid is moving because of simply transport, and it's also moving because the entire structure, the matrix, is moving. So let's use another cartoon to try to visualize these movements of fluid with respect to the solid and its total movement. So when there is no deformation, then we have this velocity of water, let's say that's this one, the blue one, due to pressure driven flow. Okay, so this is flow in relation to the solid. Now, when it is deforming, so now you can see this is the deformed shape. This is the deformed shape, and this was the original. So this is the deformed. Okay. So what you see is there is that velocity that we already talked about. That velocity of water was with respect to the solid S. And then to that we need to add flow due to this deformation of solid. So that's velocity of the solid with respect to ground. So when we combine there, then we get this velocity of water with respect to ground, and that's what goes into the transport equations. So in this last slide, we see how all the solid mechanics leading to the deformation that we did, how that couples with transport. So here is the water transport equation, and these transport equations are described in detail. They are developed as separate modules that the learner is referred to. If you need more details, you can look into those modules. And so this is the water equation, and for water equation, this is my convective term. So the velocity in this convective term is the velocity of water in relation to the solid. This is what comes from applying Darcy's law. However, if I'm standing on the ground, then the flux, the flux that we see is going to be not this rho w times vw that's in relation to the solid. So that has to be modified, and so here is the modification. So now that velocity of water is with respect to the solid S, VWS. Let me clean that so you can still see, and that needs to be modified because there is the added flux due to deformation of solid. So the added flux comes from deformation of the velocity due to deformation of solid that comes from the solid mechanics that we discussed all this time. And notice that is in relation to ground, and then multiplied by how much water is there, CW. So this is the added flux due to deformation of solid. So again, two things to note, that the transport equation gets modified by the deformation of the solid. So this is how we are including deformation, and therefore this is how we are coupling deformation with transport. So all that solid mechanics that we discussed to get deformation comes in here and modifies the transport this way. So now transport and deformation are coupled, and we solve this coupled set of equation for every phase.